Yeah.
The derivative of the logarithmic function, using the definition of a derivative as a limit, can be set up this way, the usual convention. In order to figure out what this limit is, we have to do some algebraic gymnastics with it. We have to play around with the expression and use properties of logs and so forth. We also have to get clever at some point. But let's see. How do you start it off? The first thing that you would do is you would use properties of logs. You can collapse the top here and turn that right away. Limit x log base b of x over a. Right. And then, after you do that, you have to kind of play around with this expression inside here for the purpose of which you'll see in a few minutes. I'm going to rewrite the argument of the log as, well, limit a goes to x. Instead of x over a, I'm just going to change it up and write log base b of x minus a plus a. Of course, it doesn't change the value of what the expression is. That's a legal move. But the reason being, why did I do that? The reason that that is done is so you can make a substitution in here, a slight change of variable. What I'm going to do is I'm going to invent another variable called w. We'll say let w equal this expression inside here, x minus a over a. And that trick is going to allow us to fully evaluate this limit and carry it out at the end. After choosing what to make w, we're going to rewrite what the limit is in terms of w as much as we can. So it's going to be the limit as a goes to x of log base b. What was once x minus a over a, that's going to be w plus a over a, that's 1. And on the bottom, we used to have x minus a. What can we replace that with? Well, if you take the expression, you see x minus a equals aw. So whereas we had x minus a on the bottom, we'll now have aw on the bottom. In doing so, we can actually change what the limit is as well. As a approaches x, let's see, as a goes to x, w must go to 0. So I'm just going to write that and say w goes to 0. They're going to mean the same thing. In fact, they imply each other. Because if you look out here at the relationship, as a approaches x, this side goes to 0. And so w must go to 0. Same thing the other way around. As w approaches 0, that means that this side is 0, and then a must necessarily be approaching x. We're going to need that in a couple of seconds too. But once I have this down, I'm going to rewrite this division as multiplication by reciprocal. And I'll get the limit as w goes to 0, or a goes to x, 1 over a w log base b, w plus 1. Almost there. Now, we use properties of logarithms. I'm going to take this 1 over w, bring it, the coefficient, and bring it inside as an exponent. Going to leave the 1 over a out front. What that's going to give me is limit as w goes to 0, 1 over a, log base b. If you have to bring that in, you get w plus 1 to the power of 1 over w. Now we're ready to evaluate this limit. Because as w approaches 0, we said that it was necessarily true that a approached x. So this is going to go to 1 over x. And as w approaches 0, the argument of the logarithm, this is the special limit. This limit as w goes to 0 is e, the number e. So w approaches 0, this is going to be 1 over x times log base b of, the argument goes to e. And we're almost finished. At least we dispense with the the limit notation, now it's just a matter of simplifying this. Using the change of base, this can be written as 1 over x times, we'll change it to the natural log, because we got the e in there, ln e divided by ln b. But ln e is 1, so ultimately the limit turns out to be 1 over x ln b. And that's the derivation of the derivative of the logarithmic function.